Okay, so hello everyone. My name is Frederico Bento. I'm 20 years old. Um, I'm currently studying Network and Information Systems Engineering and Faculty of Science of the University of Porto. And I should mention that this talk is not about the prevention of these types of bugs and vulnerabilities. It's more about the prevention of the exploitation of these vulnerabilities against code reuse attacks. Okay, so let's start, shall we? Okay. There are three different exploit techniques. They are code injection attacks, code reuse attacks, and data-only attacks. And I'm going to tell you what these are about, some mitigations against them, and some flaws of those mitigations, and why it's still possible to use them, and what's going to be done in the future against these types of attacks. Okay, first of all, code injection attacks. So basically, you just inject code, which also known as shellcode, into the address space of a process and transfer execution flow into it. This technique was used by LF1 first in 1996, and it was the first detailed tutorial or write-up on how to exploit these types of vulnerabilities. They were known before then, like in the 70s it was documented, but never came to the public how one would exploit these. So basically what these types of attacks do is you inject code and then transfer execution into it and executes the malicious attacker's code. And this is prevented by NX DEP, which is data execution prevention, or at the hardware level, the no executable bit. What this means is that you can't write your own code into the memory of a process and execute it, because DEP marks areas of memory either writable or executable, but never both, which means you can't write, for example, to the stack, and you can't jump into it because it's writable and it's not executable, and vice versa. So this is the stack layout and what happens on a stack-based buffer overflow. So you basically have a character array of 12 bytes. And if you copy more bytes into the space that was 12 bytes, it will start overriding variables. And once it's overwritten variables, it's going to start overriding the state frame pointer and the return address. So basically here we see the hello, it didn't overwrite anything, so everything's good. And then in the last case, we have a bunch of A's which start overriding the bar pointer and then the save frame pointer, and then that return address is pointing to the beginning of the A's. So if instead of A's, we had malicious code, it would execute that code. Obviously, in this case, it's just going to segfault. So, and code reuse attacks. These types of code reuse attacks are return to libc, ROP, which stands for Return-Oriented Programming, or JOP, which is Jump-Oriented Programming, or any other op, which is basically used by academia. They like to play with that a lot. And these are basically generalizations of return to libc. So the basic idea is to search for aligned or unaligned instructions, which are called gadgets, from executable memory and place them in a certain fashion, like a puzzle, and execute arbitrary computations. And this basically bypasses the DEP protection because you're returning to executable code and you're allowed to do that. So, and this is used in modern exploits against modern software. There's no defense yet that can eliminate this type of attacks, though there are several mitigations that make exploitation and usage of this technique very hard, or in certain cases, even impossible. These, the ASLR, PIE, SSP, and ReturnOriented are all defenses that try to mitigate this, but they have several flaws, and I'm going to show you which flaws next. Okay, so the current defenses against code reuse attacks. We have ASLR, ASLR is probably the most known defense today on operating systems against buffer overflows and memory corruption attacks. Basically, it randomly arranges the address space position of key areas, for example, the stack and the heap. So when you try to execute code reuse attacks or code injection attacks, you don't know where your code is because it's randomly, generated at runtime. And PIE helps here so that the image of the program is also randomized. By default, if you compile a program with GCC and it says that you have a full ASLR, that's not true because the text segment of your program is not randomized, and obviously it contains executable code and you can return into it and execute arbitrary computations. So PIE helps here so it also randomizes the text section. Then there is the SSP, or Stack Smashing Protector, which places a random stack canary or cookie before the saved frame pointer and reorganizes local variables. It's really important to mention that it also reorganizes local variables. It's not really known. People just think that it's a random canary that is placed. And we have the relocation read-only, which basically sets the GOT entry mapped as read-only, so you can't overwrite it. I'm not going to explain what the GOT is because that's a really different topic. But basically, you can't overwrite pointers of functions in the libc. So problems with ASLR. They are vulnerable to information leaks. For example, buffer overrides. Imagine that you have a string and it's not null terminated. If you print that string, it will throw garbage into your screen, and that's an information leak, probably some pointer to something. And for mastering vulnerabilities, we can information leak about the stack contents of the program, and then arbitrary memory reads. You can read arbitrary values from memory. The only base of the region is randomized, so if we discover a single address at runtime, we can completely de-randomize ASLR and learn the location of other data through simple equations. Basically, only the offset is always the same. So imagine that it starts at A and then you want to jump to C, and the next time it starts at B, you want to jump to D. The offset is always the same. Problems with SSP can also be leaked if we discover the canary through an information leak, simply override it with itself in a linear stack-based buffer overflow. So it does not notice that something went wrong because the canary stays intact. Imagine an arbitrary write scenario, or when you control the index of an array, simply overwrite the return address without touching the canary so it stays intact and the overflow is not detected. And also on applications that restart after a crash, example via fork, the canary can be brute forced byte for byte. So here we have how the stack canary is implemented. So this red part here, as you can see, which has a random value. Basically, it has a random value, obviously. It's not supposedly known by the attacker. And when a stack-based buffer overflow is done, it will overwrite that value. And then before popping the return address and jumping into it, basically it checks if the canary is intact. If it's not, it's because something went wrong and you have to abort the execution. So here is an idea that I came up with. It's not really new, it's just a combination of various implementations. And I'm going to tell you what is a shadow stack. Basically, what I did was XOR the return address, use a shadow stack, and variable reordering. So a shadow stack is a different stack on the memory, which is hidden by a ASLR, obviously. And you write their return addresses. So imagine that on a normal buffer overflow, you overwrite the return address, and since this same return address, the original, is stored in a different place and you can't touch it, before returning, compares if the real return address is equal to the one in the shadow stack. If it's not the same, abort the execution. If it's the same, well, continue. Basically, in function prologue, it's the beginning of the function. Every time a function is called, I XOR the return address with a random unknown value in the stack, place the actual return address in a shadow stack, also XOR same frame pointer while I'm at it, but it's not checking its integrity. I mean, I'm just protecting, okay. I'm just protecting the base pointer because it's used on data-only attacks, and I mean, while I'm at it, just do both. On function epilogue, I XOR again the XOR return address in the stack with the same value, so it's restored again, and compare with the one in the shadow stack. Then obviously XOR the XOR frame pointer again. If the return address is the same, proceed, if not abort. And variable reordering, since overwriting the return address isn't the only way of exploiting memory corruption bugs, hint hint, function pointers, and data. There are several implementations. Obviously, not make use of a shadow stack, simply XOR the return address in a register, push it on function prologue so it get lost, in a way that a linear overflow can't touch it. And also for comparison. This is described in the recent PAX team's RAP RIPROP. And the one I described previously. By using mprotect to make the hidden shadow stack read-only after writing to the return address to prevent an attacker from tampering, although unlikely because they don't know where it is. It's vulnerable to race conditions on multi-threaded programs, but near impossible to exploit. This one obviously has a high performance impact for every function call. Two more syscalls are needed. Okay, so I'm going to show you how I did this. I actually implemented patches to the GCC, but it's not here because this computer is not mine, it's Andres. And I don't even know this keyboard layout because I hate Mac. Okay, I'm just going to try it right here. Okay, so we have the test program. Basically, I'm inserting assembly, instructions. Okay, so I have the main function, which will call another function, which is right here. This is so laggy, man. Okay, so we have a buffer overflow here. I have 10-byte character array, and I'm reading 1,000 bytes into it from standard input. I'm going to show you on GDB each line and how it executes. So I'm going to break main here. I'm going to run. I'm going to step by. Okay, basically this is the push the base pointer onto the stack so it doesn't get lost. Create a new stack frame. Okay, here starts the actual instructions that I implemented. So I'm going to start showing the contents of the stack. Okay, so the next instruction is an XOR. It's encrypting the base pointer, what I'm trying to do here, with the stack pointer. Obviously, it's 0 now, so only the stack pointer will be placed, but you'll notice on another function call, this will take much better effect. So at here, I'm trying to move from the FS register at offset 0 to R12. What will get stored here is the shadow stack, which is randomized by ASLR. Okay, so we can check after I press enter what goes into R12. Okay, here we have this is the pointer to the shadow stack. And then I'm going to subtract 8 bytes from it so I can store the return address there. And then I'm going to store again the subtracted value into FSX0. So when I call another function, I can get that value subtracted, not the, so I don't lose the stored return address. Okay, so I stored it. And right here, I'm going to move the at RBP plus 8. It's the return address, and I'm just going to store that into R15. And then I'm going to move R15, which is the return address, into the shadow stack, which is R12. So the return address is there. I'm going to start showing you the stack contents. Okay, now here I am clearing out the registers so they don't get spilled. Sometimes GCC optimizations, they push the registers onto what's on the registers onto the stack, and that can be used on information leaks to de-randomize and find where the shadow stack is, and we don't want that. Okay, I'm also clearing out R12. And then this is the same implementation for the SSP. Basically, I'm getting the FS at offset 28. This is used for the random canary, but I'm using that canary, instead of placing it on the stack, I'm going to XOR the return address with this. So this is how the stack looks like down here. I'm going to execute that, and I'm going to show you how the return address looks again. I think this is the return address. This right here. This is going to change after I execute this. Okay, so I'm going to show you. Okay, this was not the return address. What was the return address? I don't remember. Okay, what changed there in the stack? Can anyone see? What is different? I'm trying to find this. Where? Okay, let me see where is the return address right here. Jesus. What? Can anybody see the difference between this stack, the contents of the stack here, and the below? There should be a difference, and it's the return address that just got XORed. No. Okay, let me try that. Yeah, probably. Yeah, true. Yeah, exactly. Yeah, you were right. I didn't execute that instruction. Here it is, it's different now. As you can see here, okay. Okay, it's not this, it's this one. These lines are different from these lines. It had 700, here it's 400, and it's clearly different. Okay, and then I'm going to XOR the racks. Okay, this is for the function. Okay, I still not reached the buffer overflow. So this is the same instructions. I'm going to pass them, go through them. Okay. I'm going to call read, and I'm going to cause a stack-based buffer overflow. I'm going to read a lot of A's, so it overflows. Okay, again, I'm getting the random cookie to array X. Fuck. I went to instructions. Okay. Basically, I did right here, I did the XOR of the racks, which was the random canary, with the return address again, which should be completely different from what it's on the shadow stack. Okay. It had 700. Okay, it's clearly not 700 because it got shorted with 414141, and it's clearly not the same, and it's going to segfault and let us know that something wrong occurred. Basically, you don't have to worry what these instructions do. Basically, I'm popping everything out of the shadow stack. This is because there are set jump and long jump buffers, which basically means that not every time, imagine that you have function 1 that calls function 2 that calls function 3. Sometimes function 3 does not return to function 2, it goes straight back to function 1. This is why I'm comparing every popped address from the shadow stack. Okay, now it's just called stack check fail, and I continue, and I get a seg fault, and I get here a message that said stack smashing detected. Okay, now I'm going to show you without the buffer overflow what happens. Okay, I'm going to, I know, this shouldn't overflow. Okay. I'm going to continue, and there was no error. It exited normally. So I'm going to exit it. Okay. Now, what we want to do is not only protect the return address, because you can overwrite other function pointers. And what we want to do is, obviously, I did this on my free time, mostly was while I was in holidays. I was, just having some fun. And I didn't have really time to do some complex changes to the GCC so I can protect the other function pointers. So imagine that we did all that and code reuse attacks were all eliminated. So there are still data-only attacks because I do not prevent the corruption of memory. I only prevent the execution, of code reuse attacks. So imagine that we have a code like this. It basically sets the affected user ID to 0 to perform some privilege operation. And then it does that privilege operation, and then it calls set user ID again, affected user ID with PWUID, which is probably to drop privileges. Now, under data-only attacks, you're going to overwrite that value with 0 again, so it doesn't drop privileges. And, the principle of least privileges, it got destroyed. So, future work. Protect all function pointers. Requires static analysis and complex changes to the compiler. Mainly GCC, which was I trying to do, and that code is just, oh my god. Conclusion. Prevention of mitigations is not trivial. Security impacts performance. Mostly the reason why these defenses and other mitigations aren't widely adopted. People prefer performance instead of security, and why this is the state we're in. And we get owned every day. So, some cool stuff. There's other research in this, which is control flow integrity, and the Intel just released a new paper on how they're planning to combat against code reuse attacks, which is CAT, which is control enforcement technology. And basically what they're trying to do is what just I implemented, but at the hardware level. So there will probably be no performance impact at all. And it's much more secure because the shadow stack will always be not writable, because they can do that at the hardware level without losing performance. And everything by Pax team is just very cool. They're the pioneers of protections of memory corruptions. They were the inventors of the ASLR, DEP, and every other, defense against the kernel. Everything. You just check out their docs and you just get, whoa, these guys are pretty great. And that's basically it. Anybody got any questions? Okay. You have a mic. Okay.
So the reason you're creating a shadow stack is basically to protect against possible information leaks, right?
No, it's not information leaks. I am trying to store in a different place pointers and return addresses so that when they are overwritten in the normal stack or heap or whatever, they get compared with the one in the shadow stack.
Why wouldn't you save, for example, the memory in the master, or basically
Yes.
So why don't you, for example, save the value of the canary not in the stack, but in the register or something?
But you're talking about SSP, Stack Smashing Protector? So can you repeat the question, please?
So you say you are creating an ultimate stack.
Okay.
Return addresses,
Mm-hmm.
canaries, and
Yes.
get stack with owner. And then when you're returning, you compare.
Mm-hmm. The original with the... Okay.
So what we're trying to achieve here is to avoid overwriting those canaries and those internal addresses.
Yes.
So to overwrite the canary, you must know what the value of the canary is.
No,
We
you
talk about brute force, but brute force in
I-
the for good canaries, but it's not.
I can override function pointers and return addresses without touching the canary. So I can simply not know what the canary is and still get code execution.
But that would imply you would skip over the canary, right?
Excuse me?
To overwrite a function pointer
Yes.
and not overwrite the canary, it would imply that you have control over skipping the canary
Yes.
and things like that.
For example, an arbitrary memory write.
Okay, okay. So it's basically just a curiosity. Why not, for example?
I
when you
mean,
compare-
SSP can get bypassed, you know?
Yeah, sure.
What I'm trying to do is, it would require knowing where the shadow stack is, which is really difficult because there's no information leaks about it, relying on ASLR, if it's strong enough. And I'm comparing them, and they get compared, and if they're not the same, you know, you just can't
But-
write somewhere you don't know.
Okay, just one more question. So
Okay.
when you're returning, you're
Yes.
unwinding the stack,
Mhm.
and I'm assuming you have a return address that you jump to compare the things. Or how are you controlling the flow? Because usually the return address is pushed onto the stack, right?
Yes.
And then you jump.
And I
jump
get
on.
that return address and I store it. It stays in the same place, but also in another place.
Oh, so your compiler is running additional code, injected
Exactly,
code.
yes.
Okay.
It's writing assembly instructions at the beginning of functions, at the end of
Okay,
functions.
so you make a call, you return, but you ensure that verifying code runs no matter what,
Yes.
even if I can override a return
Mhm.
address. Okay, cool. Thanks.
Yeah. Anyone else?
When do you decide the value of the shadow stack location?
The value?
Yeah, the offset of the shadow stack location.
You know, I was testing and I looked at the FS register always has a mapped address, a mapped area, and it's, you know, with ASLR it's always random. And I noticed that you can't, you know, overwrite past the buffer and touch it because there's unwritable areas in between, so you'll get a segmentation fault. And that's basically what I did. And there are implementations that I saw that the FS register adds some mapped memory at the random location that you can touch and you don't know because you don't have information about it. Even with the information leaks, for example, on the stack, it's nowhere there and nowhere in the heap. And I make sure to clear the registers so GCC optimizations don't push it. You know what I'm trying to say?
Yeah, I think I don't know. No, my question was, okay, so you decide the value of the offset at the preamble of the function you're calling, right?
Yes, it's FS0. Okay.
Isn't there a way? Oh, so yeah. Never mind the question. I was thinking about the information, the possibility of trying to get to the shadow stack offset.
I mean,
by
it's
looking
not
at-
impossible, but it's pretty hard because I try to leave no traces at all about where the location of the shadow stack is.
But you're going to go there on
Yes.
on the suffix of the function.
Mhm.
So if you could, for instance, try to follow code execution, like follow the instruction pointer or follow the return, no, not the return address because you just overwritten it. Never mind. Never mind.
I mean,
One more question. One more question.
Okay.
Have you looked into ARM?
Extremidade
ARM IRM
Yes.
calling convention. Have you
No.
tried? Okay.
No.
Okay, because it's different.
Yeah, it's different. I didn't try it. Anybody have more questions? No? So I hope you enjoyed this talk. If you haven't, well, you just lost probably like 30 minutes or so. And yeah, that's basically it. If you want to play with this, it's really cool. Just follow the instructions and try to manipulate this in a way that you can get code execution. It's really cool.